And we do have a name for it, right? We call this, this interval that we generate confidence interval, or CI for short. Okay, so this CI will tells you the following information. That is, at a certain probability level, right? 80% or 95% or 99% or any percentage you would like, right? So given that means, if you repeat, many times, like 1,000 times, or 100 times, just to make things simpler, right? So if, let's say, okay, let me read through this, definition before, before I sort of dissect this sentence for you. Okay, so CI, or confidence interval, it tells you that at a certain probability level, that your interval based on the sample data, right, the sample that you actually collected, will include the population mean or proportion or correlation or mean differences, whatever, right? That means, whatever feature that you're interested in about the population, right, will be included in the interval that you generate. Okay, so okay, now let's look at this sentence more closely. What it actually means is this. So this certain level of probability, let's say, for now, let's just randomly assign a value to it. And let's say that, this interval, let's make something up to make it 3 and 5, right? Just to stick to the example that we just used. And the population means 4, okay? So this is the mean that we try to guess, right? So based on the sample, because we can easily calculate the sample mean, we can sort of make a guess that, well, given that sample mean is a good estimation of population mean, we can say the population mean is probably 4. Okay? But here's the question that your boss, or other people, your reader, your audience might ask you. What do you mean by probably? Well, how probable, right? So here is, this probability comes in useful. So when we say that we're 90% confidence, or with a probability of 90.9, then my interval 3, 5, right? This is our sort of a hypothetical interval. My interval 3, 5, that is calculated based on our sample, which I'll tell you how to do in a minute, will include the population mean 4, which is based on our guess from the sample mean. Okay, so the process is like this. We collect a sample, we calculate the mean, and we say this, well, we calculate the mean to be sample mean to be 4. Because the sample mean has been proven to be a good estimator of the population mean, so we'll make a first guess, saying that because the sample mean is 4, I guess that the population mean is also 4, and it's likely, well, probably to be 4. Okay? And now the question becomes, how do we quantify this probably being 4, right? Probably being 4. Okay, so can we describe it, right? Can we describe the sentence that's based on probability? So based on certain, procedures, we can generate a confidence interval, let's say it's 3 and 5. And we say that we're 90% confidence, or there's a probability of 0.9 that this confidence interval should include the true population mean, 4. So again, right, it doesn't have to be 4, right? We're making a point guess that's 4, but by calculating a confidence interval, we're saying that it could be 4, it could be 3.2, it could be, 4.8. As long as this value is larger than 3 and smaller than 5, we're good, right? We'll have a good enough guess. So that means, and now let's understand this probability. So this probability means if we, right? So here we're drawing only one sample, okay? But the problem is, by drawing a different sample, you're very likely going to obtain a different mean, right? So let's say this is the sample mean of the second sample, And because you're likely drawing in different groups of individuals, there should be some kind of difference between this mean and the first sample mean, right? So it could be 3.8, okay? And you keep on drawing more samples, and this time you have a sample mean of 5.2, and you draw 100 samples so that you have 100 sample mean. And the last sample 100 mean will be, let's say 6.3. Okay. Now this 90 percent probability will say that once you draw 100 samples, then it must be the case, and it's very, very likely to be the case, that some sample mean would fall in this interval, whereas others, like this one, will fall above, and this one as well, right, will fall above or fall beyond this interval. But how many sample means will fall in this interval, and how many will fall beyond this interval? Well, about 90, right? Because we're saying the probability is 90, right? So we're saying given 100 samples, then 90 sample means will fall in this interval, whereas because of a randomness, there will be about 10 sample means that will fall beyond, greater than 5 or smaller than 3. Okay, so that's what this sentence means, right? That's to tell you that, in other words, this interval 3 and 5, 90% of the time would include the true population mean, right? The probability that we're interested in guessing. And this interval, about 10% of the time would not include the sample mean. So that's why we're saying that we're 90% confidence that we will have a population mean that's included in 3 to 5. Exactly what it is, we don't actually know. But statisticians and many, pollsters actually are satisfied with this interval because, as we'll see in a minute, right? Sometimes this interval, despite seemingly being sort of rough and approximate, actually can tell you a lot about the population probability that you're interested in. Okay, but anyway, this is what this sentence means, right? It means 90% of the time, this interval will include a value that's the true population mean or proportion, and about 10% of the time, this interval would not include the population mean or population proportion. Okay? Okay. But how do we calculate, what's going on here? How do we calculate this interval, right? So previously, we're making we're making up things, right? We say that, well, we randomly assign a number, 90% as our confidence level, and we make up interval 3 to 5, right, as an example. But in reality, of course, we can't just make up stuff. There's a formula, in fact, to help us calculate the confidence interval. Okay, so the confidence interval, to calculate that, we need first of all the point estimate. We also need z-score and something that we'll call standard error. So before we understand what standard error is, I will first of all draw your attention to this formula. This formula is actually not new. Okay, we have seen actually something that's very similar to this formula not long ago, and I would like to ask you what it is. Okay, what is the formula that we previously talked about and spent quite much time practicing it that actually resembles this formula? Okay. Well, you saw Z here. That should ring a bell. What is the formula for z-scores? Z-score, as we said, is a particular value right, minus the sample mean divided by standard deviation. Do you see the similarity here? Okay, so first of all, you say, well, okay, so I see a z here. There's a z here, but here is z multiplied by something, but I don't have a multiplier of z here. Well, that's easy, right? We can simply move standard deviation to here, and it will become a multiplier of z. Okay, so we can transform this formula to z times standard deviation equals to x minus sample mean. Okay, you will say, well, wait a minute. Where's this guy? Well, if we move, actually, right, this mean to the other side of the formula, we'll have m equals to x minus z times standard deviation. How about that? Now this will very much look like this formula. Because wait a minute, interval ci is an interval, whereas sample mean is only a value. Interval is a range of value. This is only one single value. That's fundamentally different. Well, congratulations, you're noticing the key difference here, but it's very easy to actually generate an interval from this formula. So here we only have x minus z times standard deviation. But what if we also add, right, a second formula that's x plus z times standard deviation? That will give us a second mean or second value, right? Now we have essentially a lower bound and an upper bound. So these two means actually will give us the confidence interval. So confidence interval, as now we see, is intricately associated with the z value. It's essentially, right, we're converting the z formula to the formula for confidence interval. Now we say, wait a minute, Andrew. Here, okay, so it appears that this formula, is it's the same for the formula for z, but we have standard error here, SE, but not standard deviation, right? That seems like another difference. Well, you're right. But it turns out standard error is just a special type of standard deviation, right? So later on, we'll tell you how to calculate standard error based on standard deviation, but for now, you just need to remember that, in fact, standard error is just a type of standard deviation. Now, right, we have exactly, we have a lower bound for the mean, and we have an upper bound for the mean based on the formula for z. Okay, and this x, remember x, when we discuss the formula for z, is a particular value from the sample, which is exactly a point estimate, right? So imagine that from the sample we don't know, imagine we put all these values into a jar, and we just stick our hand into the jar and randomly pull out a number. That will be our point estimate, actually, right? That will be our point estimate of the average value for this particular sample, right? So this is essentially our point estimate. Okay, so now you should see that this formula for confidence interval is actually an old friend, right? We have seen it before. Okay, Nothing too mysterious about it. So then what is confidence? Okay, so now let's understand this concept step by step. So imagine, right, we sort of conducted a survey, which includes the 7-point scale of opinion on gun control to a sample of Honolulu citizens. And we assume that, for to simplify the example, um, the scores, right, by these sample of Honolulu citizens are normally distributed. And we'll calculate the population mean, or actually we don't need to say that this is a population mean. Sample mean would be good enough. Okay, sample mean. So then we'll calculate the mean for the sample to be 4, and the sample standard deviation, right, to be 0.05. Okay. So this is our sort of example. Now, given this distribution, the sample mean is 4, right? And the sample distribution is, I believe, 0.5. Okay. Now, given this distribution, right? Given we say that the distribution is normally distributed, the data are normally distributed, has a mean of 4 and standard deviation of 0.5. Now, let me ask you, if I randomly draw a value from the sample, what is the likelihood that this value to be greater than 3.5 and smaller than 4.5? Okay. Again, my question is, given this distribution is a normal distribution, it has a mean of 4 and a standard deviation of 0.5. Then if I randomly draw one and only one score from the population, from the sample, what is the likelihood that this value is greater than 3.5 and smaller than 4.5? That is, will fall in this interval. That actually becomes the question of using the empirical rule, isn't it? The content that we discussed yesterday or the day before, right? So the empirical rule says 68% of the scores from a normal distribution will fall within one standard deviation above and below the mean. Okay? And it turns out if we do a simple calculation, right? So 3.5 is the x here, right? Is the x here equals to 3.5. Then let me ask you, what's the z-score associated with 3.5 in this distribution? Easy, right? We use 3.5 to minus 4, and we divide it by 0.5. That will give us the z-score for 3.5, and it is exactly negative 1, right? So this 3.5 minus 4, that's negative 5, negative 0.5, and negative 0.5 divided by negative 0.5, that's exactly negative 1. Similarly, right, the z-score for 4.5 will be equal to 4.5 minus 4 divided by 0.5. 4.5 minus 4, that's 0.5. 0.5 divided by 0.5, that's 1. There we go. It turns out that 3.5 and 4.5 are exactly one standard deviation below and above the mean. And we know from the empirical rule that the probability is 68%, right? 68% of the time, all the scores from this normal distribution will fall in one standard deviation above and below the mean, in this case, between 3.5 and 4.5. Okay? All right, this is the conclusion that we just drew. And therefore, in other words, right? We're 68% confidence, right? We're confident at a 68% level that any individual score will be between 3.5 and 4.5. This makes sense because we know that, if there, 100 scores, right? If there are 100, exactly 100 scores, from the empirical rule, we know that 68%, 68 of them, right, out of the 100 scores, 68 of them will be greater than 3.5 and smaller than 4.5. Then it makes perfect sense for us to use this percentage, right, 68 divided by 100, right, percentage, to describe our confidence level. Because in this case, right, there will be no more, no less, but exactly 60 of the 100 scores that will fall between 3.5 and 4.5. So that's why we say that we're confident at this particular level that, any individual score will be between 3.5 and 4.5. And therefore, right, the 68% confidence interval, or CI, will be 3.5 and 4.5. You see the connection here between z-score and confidence interval? Okay, let's, look at another example. So given the same distribution, right? It's a normal distribution. The mean is 4. The standard deviation is 0.5. Okay, then what's the likelihood that a single individual score is between 3 and 5? Well, easy, right? First of all, we calculate the z-score for 3. So 3 divided minus 4 divided by 0.5, that's negative 2, right? So that's negative 1 divided by 0.5, that's negative 2. And we have 5 minus 4 divided by 0.5, that's 1 divided by 0.5, so that's 2. Aha! We know from the empirical rule, right, the 95% of scores from a normal distribution will fall within 2 standard deviation below and 2 standard deviation above the mean. Okay? And therefore, we're confident at a 95% level that any individual will have a score between 3 and 5. And that's why the confidence interval here will be 3 and 5. Okay? So now we should see, right, that this confidence level has a lot to do with the z-score, right? If the z-score is 2, then according to the empirical rule, we have a confidence interval, a confidence level of 95%. If the z-score is 1, according to the empirical rule, we have a confidence level of 68%, right? So that suggests actually the confidence, right? What we call confidence in the context of inferential statistics, essentially the probability associated with z-values. Okay, so we have a z-value of 1.28, the confidence level will be 80%. If our z-value is 1.65, right, our confidence level is 90%. And if our z-score is 2, right, well, more precisely, it's 1.96, right, but roughly we say it's 2, the confidence level is 95%. And if our z-value is approximately 3, well, to be exact, it will be 2.58. But the empirical rule is sort of an approximation, right? So we say that when z-value is 3, then the confidence level is 99%. Okay, that is, we're almost certain that all values from the population, from the sample, will be within 3 standard deviation above and below the mean, right? So given this, formula, right? So CI equals to sample mean. Now we're talking sample mean. as the point estimate here, um, plus and minus z timed standard error, right? Or standard deviation, right? Doesn't matter. So let's say, given this, formula, you want to be confident at an 80%. Okay, you don't need to be very confident here. It happens when, for example, you're given the first trial to answer the question, right? You want to sort of explore all the possibility here. You don't, and the result is not that important. So, it's okay, right, to assign a low probability to it. So then you will use accordingly a z-value of zero point 0.8, right? But if this result is very important, you want to be more confident with your estimation, then you will choose a higher probability level. Then you will use z equal to 2, right? And this is indeed the most commonly used confidence level. Okay, so that's how we sort of will choose confidence levels and the z. Okay, so now given this formula, now we have the z-score, right? Z-score we can choose from this table. So that's one known value here. So what we don't know then will be, what is the sample mean, or what is the feature point estimate, right? We're trying to make inferences about, and what is the standard error here, or standard deviation. So these will be the two unknown values we need to calculate from the sample. Once we, from the sample, calculate the mean and calculate the standard deviation, and then we can choose according to our needs the z-value that we need, and then we can easily calculate the confidence interval. Okay, so now I will be teaching you how to obtain these two values with concrete problems. So let's start with sample proportion.